Hello, this is Dr. Hassan with Innovate, and this is lecture number 54, VHDL Design 7 of Chapter 8, Analysis of Synchronous Sequential Network of the course Digital Logic Design and Digital Systems and Digital Electronics. This is the last lecture of Chapter 8. This is a disclaimer for you to read. I cite 3 references in digital logic design, however, there are many books related to the subject. In Chapter 8, we covered models of synchronous sequential networks, especially the Mealy, the Moore, the Medvedev, the mixed Mealy-Moore model, and we discussed which model is the best. Then we covered the analysis of sequential network using state graphs or tables, or by signal tracing or by deriving the state graph. And in this lecture, which is the conclusion of Chapter 8, we will talk about VHDL design and how to design VHDL codes to analyze or to build synchronous sequential networks. VHDL codes for synchronous sequential networks are divided to 2 types of codes. 1 process VHDL codes and 2 process VHDL codes. In 1 process VHDL codes, each states in the state graph of a finite state machine can be translated to a case in a case-when construct. The state transition can then be specified in if-then-else statements. We begin by defining the enumeration type consisting of state names and declaring a signal of that type as follows. We say state type is S0, S1, S2, S3. If we have for the state signal, state type, we declare the signal state to be used within the program. In FSM, with a large number of states, the signal state can be declared as an integer. In the architectural statement for n state FSM, one can declare state as follows. Signal state, integer in the range 0 to n, where n is the number of states, where n is the maximum number of states. Next, it is required to specify transitions between a state and the finite state machine. This can be achieved by declaring a process statement that describes the finite state machine as a sequential network. The input signals that can cause the process to change are clock and reset n, this is an active low asynchronous reset input. Hence, these signals must appear in the sensitivity list of the process statement as follows. So process, we say clock, reset n, begin, then we end the process. One may choose a process statement without a sensitivity list as follows. We say process, begin, wait until the clock is 1, then we'll follow the description of the machine, then end the process. Within the process statements, we define the state transition using case. State is when S0, for instance, if X is 0, then we will stay in S0. Or we have an assignment statement where we assign to the variable state S0. Else, the variable state, which is STATE, will be assigned S1 and F. And we continue describing the machine state by state, when S0, when S1, when S2, and so on and so forth. Then we end the case. If we prefer to declare the appropriate number of flip-flops and the state assignment for the state S0, S1, S3 to Sn, an attribute declaration is used. We do it this way. State type is S0, S1, S2, S3, attribute enumeration code string. Enumeration code of state type is 00011110, and this is actually double quote closed with double quote. Signal state type. Now with this, actually S0 will be 0, 0, S1 will be 0, 1, S2 will be 1, 1, and S3 will be 1, 0. So we will choose our own state assignment. If we don't have this declaration, actually the machine, the program, will choose a state assignment as appropriate. Now the two-process VHDL codes, on the other hand, has advantages over the one-process code as follows. In the one-process VHDL code indicates that the next state assignment will be based on the present input, but does not indicate when the next state becomes the present state. This happens synchronously on the rising edge of the clock in a second process statement. Therefore, in a two-process mod machine or Mealy machine, we declare two signals, present state and next state. State type is S0, S1, S2, S3, signal present state, and next state, state type. So here we don't declare the signal as only state, STATE. We have present state and next state. The first process statement declares all possible transitions between the states using case-when statements. The sensitivity list of the first process statement consists of the present state and the input sequence X as follows. We say process X, present state, we begin in the process. In the second process statement, the next state becomes the present state upon the rising edge of the clock. Hence, its sensitivity list consists of the clock and reset, and as follows. Process clock reset underscore and again, if reset n is 0, then S0 will be assigned to the present state. So it means that the machine will reset to all zeros. Else, if clock event and the clock is 1, then the present state will be assigned with the next state, or the next state will be assigned to the present state. And if in the process. Now clearly the reset n is asynchronous because it will take place before the clock. Let's take a Mealy example, Mealy synchronous sequential network using one process. In this Mealy with one process VHDL code, the sequential network has one input X and one output Z. The output Z is 1 if and only if the number of ones received is divisible by 3. So if S0, if I receive 0, the output is 0 and I will stay in S0. If I received 1, the output is 0. I will be in S1. If I'm in S1 and I receive another 1, the output will be 0. But if I receive, and I will be in S2. If I'm in S2, I receive a 1, the output will be 1. So we have 3 ones divisible by 3, and I will get a 1. So the output will be 1. So if we continue generating ones, inputting ones, okay, and we will continue outputting what? Outputting 1. So in the second round, we will have 6 ones, which is divisible also by 3. Then 9 ones, and we will get Z will be 1. So this machine is a quite simple machine, and let's see how the code will look like. Library IEEE use IEEE standard logic 1164 entity Mealy 1 is both. I will define clock as an input, X also as an input. I can add clock comma X if I want to, Z as an output in a standard logic. In Mealy 1, architecture behavior of Mealy 1S, I will declare state type is the states that I have, S0, S1, and S2. I have 3 states. Signal state type. Now the state is a variable state. Begin, the process begin. Wait until the clock is 1, case state. Now when S0, if X is 0, then I will assign S0 to the variable state, and I will assign 0 to Z. Else, S1 will be assigned to the variable state, and also 0 will be assigned to Z. So I'm really describing the, so if S0, if I receive 0, the output will be 0, and S0 will be assigned to the variable state. Else, I will go to S1. S1 will be assigned to the variable states, and the output still is 0. So describing the graph one by one in the case statement, state by state. Okay? And if when S1, therefore, if x is 0, then I will assign S1 to the state and 0 to Z. Okay? Else, I will assign S2 to the variable state and 0 to Z. And if when S2, if x is 0, then I will assign S2 to the state. I will stay in S2 and 0 to Z. Else, I will go to S0, so S0 will be assigned to the variable state, and 1 will be assigned to Z. And if. So actually, this is the VHDL code for the state graph, state after state, in sequence. So I started with case, I have to end case. Case state is, I have to end case. In the process, because I started the process, I have to end the process. And in behavior. In behavior, it means I'm ending the architecture statement behavior. And this will be the complete code. Now the code is slightly improved with adding reset n. So if I add reset n, the state always, the machine will reset to a 0. It means the output of all the flip-flops will be zeros. Since we have 3 states here, we will have only 2 flip-flops in this machine. Okay, so the code with the reset n, here I define Mealy 2, the port clock X, reset n, all of them input, and Z output in standard logic. In Mealy 2, architecture behavior of Mealy 2 is type, state type is S0, S1, S2, signal state type, begin, process, sensitivity list, reset n, and a clock. We begin. If reset n is 0, then I will assign a 0 to the variable state. Now, else, if I have a clock event and the clock is 1, this is the positive going age of the clock, then case state is. Those statements are identical to the previous program. I will describe my state graph state after state. So I will, when I'm in S0, if x is 0, then I will assign a 0 to the variable state and 0 to the output Z. Else, I will assign S1 to the variable state and 0 to the output Z. And the same thing with S1 and S2, and if in the process and in behavior. So in this code, we only added really reset n to the code, and this is asynchronous reset to the whole machine, and it is active low asynchronous, and this is why we'll have to take place before the statement of the clock. Slide here. Okay. Now, sometimes we have a large number of states in the machine. So how we can go through every state as we did in the case statement, or we can actually do the following. When the state declaration has an integer number, one can combine many states with identical performance in one case when statement by separating each 2 states with a pipe. So if we say when 0, 1, 2, because if you look here, S0, when I have 1, the output will be 1, I will go to S1. Okay, so S1 will be, I'm incrementing S0 by 1. The same thing, I go to S2. Okay, so if I have 1, if X is 1, I will go to S3, and so on. What if X is 0, I'm staying in the state. Okay. So by doing this this will assess all these states by all performance until I reach S14, all of them by all performance. They are similar performance, or they have identical performance. So in S14, I cannot increment S14 to S15, okay, because I started with a 0, I will end up with S15. But S15 we can, if S15 is not identical to S14, because S15, if we add 1, will be a 16, and I don't have a 16, I have a 0 because I started with 0. This is a mode 16 counter from a 0 to S15. So I will leave S15 outside the when statement. Okay, so we'll see as follows. So library IEEE use IEEE standard logic 1164.0. Entity Mealy 3 is port. We have clock XN in standard logic, and we have done as an output in standard logic. We define done as an output from the machine. And Mealy 3. Architectural behavior of Mealy 3 is signal state. This is a variable state, integer 0 to 15, because I have 16 state. Begin, process begin. Wait until the clock is 1. Case state is when 0, pipe 1, pipe 2 until 14. Then, if x is 0, then state will be assigned to the state. It means I'm remaining in the state. Okay? And done is 1. Done is 1, which is the output. The output, we called it done. We didn't call it Z, we called it done. Okay, see the output. If I'm staying in the state, the done will be 1. So the output in every state, if the input is 0, the output will be 1, which is we called it done. Else, state plus 1 will be assigned to state. So if I am in S0, I will go to S1. Okay, and also done will be equal to 1. So if I am in S0, and if the input is 0, the output will be 1, which is done. If I am in S1, which is state plus 1, the output will be also done, which is equals to 1. So if the input 1, okay, so done will be always 1. If x is 0 or x is 1. Okay, so accordingly, we will increment the state by state plus 1, and done will be 1. And but when I am in 15, if x is 0, then 15 will be assigned to state. Okay, and done will be 1. See why I didn't add 15? Because I cannot say I'm going to 16. I don't have states called 16. So 15 will be assigned to the state if x is 0 when I am in 15. If x is 0, but if x is 1, I will go to state 0. So state 0 will be assigned to state. And done also will be 0. At that time, done will be 0 to indicate the termination of the count. So the last done, which is 1/0. This is the only difference here. So done will be 0. Done will be 0 if I'm going to state 0, done will be 0. Okay? Done will be 0 when what? When x is 1. So else 0 will be assigned to state and 0 will be assigned to done. And if, in case, in the process, and in the architectural behavior. And this will give me a mode 16 counter. Okay, and I know that I reached the final count when done will be 0. Otherwise, done will be 1 all the way. Now, the next example, we will take actually more sequential synchronous network with one process. The figure represents a more finite state machine, or SSN, with one input X and one output Z. The output is 1 if and only if the input sequence is an even number greater than 0 of consecutive ones. So if I'm in S0 and I receive 1, I will go to S1. If I receive another 1, I will go to S2 and the output is 1. So I have an even number of consecutive ones. If I am in S2 and I receive another 1, I will go to S1. If I receive another 1, I will go to S2. So I will have 4 ones now. And the output Z will be equals to 1. 3 states, S0 with an output 0, S1 with the output 0, and S2 with output 1. And when I have 2 consecutive, 2, when I have even number of ones greater than 0, the output Z will be equals to 1. So even number of consecutive ones, the output Z will be equals to 1. So the machine works nicely as a state graph. We'll see how the code will look like. I want to process code, again, library IEEE, use IEEE standard logic 1164 entity. Mode 1 is we define the clock and X as input and Z as an output. In mode 1, architecture behavior of mode 1 is type, state type is we define the state S0, S1, and S2. The signal, the variable signal which we define state, which is a state type, we begin. Process, clock. The sensitivity list here is a clock because I don't have reset n. If I have reset n, I should add it. Begin. If a clock event, case state when S0, if X is 0, then I will assign S0 to the variable state, else I will assign S1 to the variable state. And if when S1, the same thing with S1, I will assign S0 when in S1, if X is 0, I will assign S0 to the state, else I will assign S2 to the state, to the very end if. When S2, therefore, if X is 0, then I will assign S0 to the state, else S1 will be assigned to the state end if, end case, end if, end the process. Now Z will be assigned to 1 when state is equals to S2, else will be assigned to 0 in behavior. So in mode we define the state, since the state really is, the output is 1 only in one state, which is S2, else Z will be 0. So in behavior, and by doing this, we finish the code, okay, for the mode network. Now the next example, the only addition here, I added reset n to reset the whole network to a 0 if reset n is activated, which is active low. And this is asynchronous, so it has to take care before the clock. See, as you see, I added, the only changes occurred, I added reset n as an input in standard logic. And in Mealy for architecture behavior, I declared the states S0, S1, S2. I declared the signal variable state as a state type we begin. Okay, and in the first process, this is a two-process code. In the first process, I will have the process reset n and clock. Okay, I will begin. If reset n is 0, then S0 will be assigned to the state. Else if I have clock event, which is a positive going edge, then actually the case state, then I will define the state graph. When S0, if X is 0, then S0 will be assigned to the state, else I will go to S2, and if the program continued, when in S1, if X0, then S1 will be assigned to the variable state, otherwise we'll assign S2, and if when S2, I will assign S2, if X is 0, I will stay in S2, else I will go to S0, and if, in case, and if. Now, in the process, in the second process, okay, what I have, the sensitivity list will be state and X because those are the two variables to be used. Case state is when S0, Z will be assigned to 0. When S1, Z will be assigned to 0. When S2, Z will be assigned to X. And this is why X is used as a sensitivity in the sensitivity list. Why that's true? Because when we are in S2, okay, if X is 0, if X is 0, Z is 0. If X is 1, Z is 1. So if I am in S2, I will assign Z with the value of X because Z will be equal to X in case, in the process, and in behavior. So we have seen actually this machine, the Mealy machine, with one process and two process codes in two different codes, and both they will work nicely. Okay, you can use it for simulation or for synthesis. We'll do the same example that we did with one process. Okay, this machine with two consecutive even ones, Z will be 1. So this machine with the reset n, we did it with one process code, and we will do it with two process code as well, as follows. Library IEEE. Use IEEE Standard Logic 1164.0. Entity mode 3 is we have clock reset n x as input and z is output. In mode 3, architectural behavior of mode 3 is we declare the type. State type is we have 3 state S0, S1, and S2. We declare the signal to be present state and next state type. We begin. The first process statement, we have the sensitivity list X and the present state. We begin. Case present state is when S0, my present state S0 of X is 0, then S0 will be my next state. So I will assign S0 to the next state. Else, I will assign S1 to the next state. And if. Now, when I am in S1, if X is 0, I will stay in S0 to be my next state. Else, I will go to S2. And so S2 will be my next state. And if I am in S2, if X is 0, I will stay in S0, so S0 will be my next state. Else, S1 will be my next state. And if, end case, end the process. The second process statement will have the clock and reset n. In this case, my sensitivity list, we begin. If reset n is 0, then S0 will be assigned to the present state. Okay, it means this will be asynchronous because it's before the clock, and this will reset the whole machine to all zeros. Else if I have a clock event, which is a positive going age, and the clock is 1, then next state will be assigned to the present state. And if in the process, then Z will be assigned to 1 when S2 is the present state, else will be 0. So if I am in S2, okay, as present state, when S2 and present state equals to S2, Z will be equal to 1. And this is the only way when Z equals to 1 and I am in S2. So Z will be equals to 1. And this will be the end of the 2 process code for the mode machine with even number of consecutive ones. So we did this with one process code and with 2 process code. And again, you have the choice of choosing either one. This is the end of this wonderful lecture about writing VHDL code for synchronous sequential network by United States machines. And I thank you very much for listening. Please subscribe by clicking on the blue circle. And sincerely, Dr. Hassan, hopefully to see you soon in the next lecture.